Electrical conductivity and net ionic equations are the two concepts that this podcast will introduce. The connection between the two of them lies in understanding that electrical conductivity of aqueous solutions comes about with ions that are free floating and free moving in solution. And so the more ions that are present, the brighter the light bulb. So more ions, brighter bulb. Fewer ions, dimmer bulb. By looking at the two equations shown here, you can actually see that since the light bulb is bright in the picture on the left, that what really predominates in solution is not sodium chloride as a distinct unit, but sodium ions and chloride ions predominate. So they are found on the product side. On the other hand, in the second diagram, what you will find with a dimly lit light bulb is that very few of these molecules of acetic acid are broken apart into ions. So with fewer ions and mostly molecules present in the solution, the reactant side is what is prevalent to a greater degree. This is something that we can't tell when we're first learning this concept by looking at the formulas of reactants and products, but a demonstration was done in class this week, and you were asked to form some conclusions about what you observed. So that's what we're going to talk about now, is some of the conclusions. So we have strong, weak electrolytes and other substances that are classified as non-electrolytes. And through the course of the demonstration, you found that substances such as sodium chloride, potassium iodide, copper sulfate, were strong electrolytes. But something such as acetic acid was a weak electrolyte. And then finally, you also found that something like sugar and also rubbing alcohol were non-electrolytes. In other words, that was an indication that there were no ions in solution and only molecules were present. Going to the next step of looking at overall balanced equations, this example of a double displacement, and a second example of a single displacement reaction. In both cases, what you see are all of the chemicals involved in the reaction, but what you don't see is very clearly is that all of the starting material does not change into new products on the product side. And that's the purpose of moving away from an overall equation and eventually talking about something called an ionic equation, and then finally a net equation. A net equation is really the bottom line. So, for example, if you look at your net pay from a paycheck, if any of you have a paycheck, your net pay is the money that you get. That's what's most important. So when we're writing a net equation, which is what we'll get to in just a moment, all we do is remove out the ions that were uninvolved in the reaction. These ions have a special name. We'll come back to them. Perhaps you have an idea of what they would be. So going to this double displacement reaction, if we're going to write an ionic equation, then what we want to do is remember which molecules are written because they are soluble in water and ionic compounds. Which ones do we write as molecules of this four, and which do we write as ions? So let's go back to the list over here, and we find that soluble ionic compounds we write as ions, but insoluble ionic compounds we write as molecules. So going back to this equation over here, we can see that silver nitrate is aqueous. We're going to write that as ions. Sodium chloride, aqueous. Sodium nitrate, aqueous. But silver chloride, because it is a precipitate, the solid that forms from the chemical reaction, we're going to keep that together as a molecule. Stop the podcast and try to do this on your own. That's the best way for you to practice if you understand what I'm talking about. How did you do? So I have silver ion. I remembered the positive charge, the nitrate ion, sodium, chloride ion. Each time I'm putting the proper charge on the ion using formula writing skills. Notice that I did not break apart silver chloride into ions. That is because silver chloride is a solid that formed, the precipitate that formed. This was from, I believe, one of the stations in your chemical reactions lab. Notice that on one side of the equation you see a nitrate ion, and also on this side you see that the nitrate ion doesn't seem to be changing at all, and there's a second ion, the sodium ion, is unchanged. So when we take this ionic equation and then we move to trying to find the net equation, what we're going to do is eliminate those ions that are common as ions to both sides. And when we eliminate those, we're left with the net equation. Silver ions plus chloride ions yield silver chloride. And so, yes, they're called spectators. These ions are kind of like watching the chemistry show going on here. Silver ions plus chloride ions yield silver chloride is the net equation. It takes the larger equation and simplifies it down to what's most important. What has changed? The sodium ion and the nitrate ions remain unchanged. This is the general format for any double displacement reaction. I think single displacement is a little bit more complicated because you have ions turning into elements that are neutral, and so that process is a little bit more complicated, so let's walk through it together. On the reactant side, you have silver nitrate, which is aqueous, and elemental copper. Is copper neutral or charged at this point? Hopefully you know that it's neutral. And on the product side, we have an aqueous solution of copper nitrate. So if we go back to our rules, we see soluble ionic compounds are written as ions. How did you do? Silver ion, nitrate ion, coming from the silver nitrate. Whoops, looks like I forgot to put in a coefficient of 2 because there were 2 silver nitrates, so that means there's 2 silvers and 2 nitrates. 1 copper, I bring that down. Notice I did not put any charge on the copper metal because it is neutral in its elemental state. On the product side, we can see that copper ions are formed from copper metal. Wow, that means the copper must have done what to go from neutral copper to copper plus 2? You guessed it, it lost 2 electrons. Nitrate ion, coming from the copper nitrate, bringing down the 2, and then bringing down the 2 for the silver. Notice the silver on the product side is neutral. It's in its elemental state. So that means the silver ions gained electrons. There were 2 of them, so each one gained 1 electron to become neutral. So if we can look at this equation, what is common to both sides that we need to cancel out? Well, this gets a little trickier here. Notice that there's 2 silvers on this side, but they're +1. And on the product side, these silvers are not charged. They're neutral. How do we know they were neutral? This was the element, the new element that was formed. Remember, in single displacement reactions, we have an element plus a compound. The copper displaces the silver, so the silver element is neutral. So we can't cancel out the silvers. Nitrate looks like it's common to both sides. I forgot to bring down my 2 again, but I think you get the idea. So we can cancel out the nitrate. Is there anything else we can cancel out? Well, we see copper on the reactant side, but that copper is neutral and this copper is an ion. Can we cancel that out? And the answer is no. What we're left with, the net equation, is 2 silver ions plus 1 copper metal yields 2 copper plus 2 and 2 silvers. The spectator ion in this case is nitrate. Often, not always, in double displacement there are 2 spectator ions, and in single displacement there is only 1 spectator ion. Not always the case, but it's a good thing to help you remember. A couple of other things I want to call attention to. When you finish this equation, you'll notice that not only are the atoms balanced, meaning there are 2 silver on the reactant side and 2 on the product, and 1 copper and 1 copper 2 plus on the product side, but also there's conservation of charge. If you look at the total charge on the reactant side, we see 2 plus neutral, so that's a total of 2 plus on the reactant side, and if we go to the product side, the total charge is 2 plus as well. You will have conservation of atoms and conservation of charge. If you don't, you've probably forgotten an ion somewhere. I hope these 2 examples will help you work on net ionic equations. View this and try to do 5 double displacement and 5 single displacement net ionic equations. Always do the ionic before the net, and bring those with you to class after watching this video. We'll go over them in class tomorrow.